Okay, so remember last week in the last lecture, we introduced Euler's formula for planar graphs. Right, and so let's just recall what this is. And so for the lecture today, we'll be talking about some applications of the formula. But before we do that, let's just review what the formula is. And so remember, you have G as a planar graph, meaning it's a simple graph that's connected and you can draw it on the plane without any of the edges crossing, right? So it doesn't mean that every possible way to draw it doesn't have edges crossing. It just means there's at least one way to draw it that does not have edges crossing, and then it's planar. And so remember that if you can do this, you can make sense of different regions that the graph separates the plane into, right? For example, maybe this is my graph. My graph G. This is certainly a planar graph when I'm drawing here, right? So let's say this is G, excuse me. And so, right, remember this graph separates the plane into different regions, right? So maybe this is R1, this is R2, this is R3, right? The regions are encircled by different circuits in the graph. Right, and so even though I have this edge in R3 that's sticking out into the middle, this whole region is still counted as just R3. And then remember, we want to also signify the outside region, or the region that's outside the graph, so I'll call that R4. And I'm going to let R equal the number of regions, right, little lowercase r. And so for this example, the R is 4, although in general, of course, it could be a variety of different numbers. And then so remember that Euler's formula says that the number of regions is equal to the number of edges minus the number of vertices plus 2, right? So this is number of edges. This is number of vertices, right? And that's right. Right, so in this case, we have 4 regions and we have, well, we have 8 vertices. And so also we have 1, 2, 3, 4, 5, 10 edges, so the math works out, right? So you can check that it works out for this example. Right, and so what we're going to do is see how to apply this formula to determine a variety of results related to planar graphs and also graphs which are not planar. And in particular, we'll see how you can use Euler's formula to show that certain graphs are not planar. Right, and so in order to make this work, we have to introduce a little bit more, or a new quantity related to these regions. And so in particular, we're going to talk about briefly the notion of the degree of a region, right? So previously we had talked about degree of vertices. It turns out you can also define the degree of a region. And there is a relationship between these two definitions, although we won't go too much into that for now, right? So, well, what is the degree of a region? So the degree of a region, say, let me call it capital Ri, in a planar graph, right, so it's going to be the number of edges on the boundary of the region. With one additional property to take care of some exceptional cases, which I'll mention in a second. Right, and so, for example, if I look at the picture above, let's look at the region R1. So what is the degree of R1? Well, I just look at the number of edges that make up the boundary. So you can see that there's 4 distinct edges that form the boundary of R1. So the boundary of R1 is going to be 4. You do have to be a little bit careful, because what about edges like this edge that you can see? Let me just highlight it with red. Like this edge that I'm currently highlighting with red. What about this edge that's kind of sticking out of the graph? Well, if I look at the region R4, how do I count this edge when I'm counting the number of edges that are on the boundary of R4? Well, it turns out that we're going to want to count this twice. And so the book doesn't use this terminology, but let me call this, just so that we can have a precise way of talking about this, let me call this an isolated edge. Right, so isolated edge because it's not forming a circuit, right? So there's another one over here as well. I'll call this an isolated edge. Again, an edge that's kind of sticking out, maybe like a peninsula or something like that, and it's not forming a circuit. So I just want to add on that we count isolated edges twice, right? Towards the degree of a region. Right, so if you have an isolated edge on the boundary of a region, that will count 2 towards the overall count. And so where's an example where this shows up in the picture above? Well, if I look at, for example, the degree of R3, right? So if I look at the outside triangle that bounds the region R3, there are 3 edges there. And I also have this inside edge that's isolated, which I'm going to count twice. So the degree of this is going to be 3 plus 2, which is 5, right? And the 2 is coming from the isolated edge. Right, so it's not 4, it's 5. Right, and so similarly, what if I want to find the degree of R4? Well, I have one isolated edge, so that's going to count 2. And then all the other edges that are on the boundary of R4 are, well, if you look at this, if you ignore the one isolated edge that's sticking out into G4 and you just look at the sort of like the shell of the remaining part of the graph, counting all the edges on that outside boundary are going to be contribute to the rest of the count of the degrees. So let's see, there's 6 of those, right? And so the overall degree of R4 is 8. Okay, and so this notion of a degree of a region is going to help us in applications of Euler's formula, right? Because in particular, remember, our Euler's formula is about the number of regions, and so this extra bit of information will help us in some analysis. Right, and so what I'm going to do now is fix a planar graph G. I want to elaborate on this a little bit more. And so I'm going to let lowercase r sub I be the number of regions in G of degree I. Right, I mean, for example, if I is equal to 3, R3 is the number of regions of degree 3. It may turn out that the graph has no regions of degree 3, in which case R3 would be 0, which is allowed. Right, and so if, as before, we let R equal the total number of regions, then notice we can write R as a sum of each of these individual things, right? So the number of regions of degree 1 plus the number of degree 2 plus the number of degree 3 and so on. And moreover, also note that, well, let's say I add up all the possible degrees, right? So I sum up the degree of each region where R, right? So this is a sum over all possible regions. It's a finite sum in the graph. Well, one way I can organize the sum is by, well, I have for every region of degree 1 that contributes a count of 1. And so since I have R, one of those, I'll have that number. Now for every region of degree 2, it contributes a count 2 towards the sum. So I'll have 2 times R2. Every region of degree 3 contributes a count of 3 towards the sum of all the degrees. So I'll have plus 3 times R3 and so on, right? Plus 4 times R4. Right, so when I write down these dots, I don't mean it's an infinite sum, right? So it's going to stop eventually. I just want it to be kind of arbitrary because I don't know how many regions there are, but the graph has some finite number. But right, and so the idea is you continue this pattern until you hit the largest possible number of regions, and then you stop it. Right, and so what we're going to do now is relate this sum to the number of edges in basically the same way. If you think back to one of the first lectures on graph theory, in the same way we related the degree of vertices to the number of edges. right? So let's say as above that the number of edges is equal to E. And so the claim is that if I multiply 2 times E, right, if I multiply the edges by 2, that this is actually the same as the sum of all the degrees of over all the regions. Right, and so what you want to do here is think of what we call the handshaking theorem, which was the analog of this result, except when I looked at the degrees of the vertices rather than the degrees of the region. And so why is this true? Well, each edge, let me call it, say, E sub I, contributes. Well, if I think about how much each edge contributes to the count of the overall degrees of all the regions, when I add them together, each edge has to contribute exactly twice, or exactly 2 to the count to the overall sum of the degrees of the regions. Right, and so why is this the case? Right, so there's 2 cases to consider, right? So maybe this is let me draw my edge here, right? So maybe there's some region A and some region B, and my edge is separating these 2 regions, right? So in this case, the edge contributes 1 to the count of the degree of RA and 1 to the count of the degree of RB, and so it contributes 2 overall to the total count. So that's one scenario. The other scenario is, well, what if we had an isolated edge, right? So what if my graph was something like this, and maybe this is my EI, which is isolated in the sense described before. Well, then there's the region that's outside the graph, which I'll call maybe RC. But remember, we said that this edge will count twice towards the count of the degree of RC. And so this is one of the reasons why we make that assumption, which is so that this formula is still valid. Right, and so in both cases, in case 1, it contributes 1 to the degree of RA and 1 to the degree of RB. In case 2, it contributes 2 to the degree of RC. And these are the only 2 cases, right? And so in any case, it'll contribute exactly 2, right? So we have this sum, right? And so this is like the version of the handshaking theorem, but for regions. Right. And so how are we going to take advantage of this? Well, I have to define one more thing. So I'm going to let, remember, we have some fixed graph that we're working with. This will apply generally to planar graphs. So I'm going to let r, little lowercase r with a bar on top of it, I'm going to let this be the average degree of the regions, of the average over all the degrees. And remember, G is a planar graph, right? This stuff only makes sense if G is planar for now. Right, and so what does it mean that it's the average? So this means that R bar is equal to the, well, I have, it's an average, so I want to write it as a fraction. So it's equal to the sum of the degrees, right? So I add up all the degrees of all the regions. And I'm going to divide that by the total number of regions. Right, and so more precisely, well, in the denominator, I'm just going to put R because that's the total number of regions. And in the numerator, I'm going to put the sum of the degrees, sum of all the degrees, right? But remember that if we sum up all the degrees as R varies over all the regions in the graph, we just show that that was equal to 2E, right? So this tells me that the average number of regions is equal to twice the number of edges divided by the number of regions, right? Using the formula we just derived on the previous page. Right. And so what we're going to do now is use this formula along with Euler's formula to prove a few things about two particular graphs. And so we're going to prove the following theorem, which is again going to be a consequence of Euler's formula. So I'll have 2 parts. The first part is we're going to give a different proof that the complete graph on 5 vertices, which is K5, is not planar. And we're also going to give an argument that shows that if we look at the complete bipartite graph with 6 vertices, or k3 comma 3, we're going to also show that this is not planar. Right, and so how is this going to work? Well, let me first begin by proving the first part. So let's look at part 1. Right, well, for k5, remember that the number of vertices is equal to 5. And since for the complete graph, there's an edge connecting every pair of vertices, the number of edges has to be equal to 5 choose 2, right? Because for every pair of vertices, or every choice of 2 vertices, you have an edge connecting it. So that's equal to 10, right? And so what we're going to do now is do something, we've seen a few arguments like this, which is a proof by contradiction. So we're going to suppose that it was planar, or suppose it had a planar representation. Well, if it's planar, then Euler's formula applies, right? And in particular, Euler's formula says that if R is the number of regions, then R has to equal E minus V plus 2, right? Or 10 minus 5 plus 2. And so in particular, we would be able to draw, if it were planar, we would be able to draw it in the plane such that this graph had exactly 7 regions. And what we're going to do now is plug this into the previous formula for the average, or this formula for R bar, and we're going to obtain something that's not possible, and therefore it can't be planar. So let's do this now. Right. Well, recall from above that the average degree right, so I have a formula for the average degree, so it's equal to 2e, twice the number of edges divided by the number of regions. Well, we just saw that there are 10 edges, so there has to be 20, 2 times the number of edges is 20, and then we saw that the number of regions is 7, right? And so this tells me that the average degree of the regions in the picture that we drew has to be equal to 20 over 7. However, notice that 20 over 7 is strictly smaller than 3, which is just a calculation you can do. Just look at the decimal expansion, for example. Or just note that 20 is smaller than 21, and 7 times 3 is 21. That's maybe an easier way to see this. And so therefore, we're going to claim that there has to be, since the average is smaller than 3, we're going to claim that there has to be a region of degree 2 or less in the graph. Right, so of degree less than or equal to 2. Well, think about it this way. How could there, right? Suppose there were no region of degree less than or equal to 2, right? So otherwise, all the regions would have degree bigger than or equal to 3. But if all the regions have degree bigger than or equal to 3, then when I take the average would have to be bigger than or equal to 3. Right? So the average degree, R bar, would be bigger than or equal to 3. But that's not the case, right? Because of this formula, we just showed that it's smaller than 3. And therefore, there has to be at least one region of degree less than or equal to 2, right? And again, this is just the idea that if I average a bunch of numbers that are bigger than or equal to 3, then of course the average is going to be bigger than or equal to 3, and that's all we're using here. Okay, and now I'm going to claim that this can't happen, right? So we just discovered that there has to be a region. Well, this is no longer a claim, so let me release this, or erase this. And so I'm going to claim now that it's impossible for there to be a region of degree less than or equal to 2, right? For K5. Right, and so why is this the case? Well, what does a region of degree 2 look like? Well, if I have 2 vertices, then it'll just look like this, right? So if I have in this case, if my graph only has 2 vertices, this is a region of degree 2. Another way that this can happen is, well, what if maybe my graph is something like this, which I'm not going to draw, and then I have right? So maybe the graph has some circuit on its boundary, which I'll draw informally to indicate that like there's a lot of stuff going on that I'm omitting, and maybe R1 is on the outside and this is my edge. But this region can have degree 2 because there's a bunch of edges out here that are going to contribute to the degree. So the degree is going to be bigger than 2. Right. The degree of the region, unless you had fewer vertices, right? So so this is true if number of vertices is bigger than or equal to 3, which is the case for our graph. And so therefore, since we arrived at this contradiction, it follows that K5 can't be planar, right? We didn't show that something weird is going on. We just showed that under our hypothesis, something weird happened, and therefore the hypothesis has to be wrong, right? And so therefore, K5 is not planar. Otherwise, we get this contradiction. Right. Okay, and so that's the proof of part 1. Let me also do is the proof of part 2, which is very similar. So now let's prove part 2 of the theorem. And so remember here, we wanted to show that the complete bipartite graph K33 is not planar, right? And so remember, what does this look like? Well, I have 2 sets of 3 vertices, and in each of the 2 sets, each vertex is connected to everything in the other piece and nothing in its own piece, right? So it's going to look something like this. Right, so that's K33. And so now we want to show that this is not planar, right? Well, how many vertices do we have? We have 6 vertices. And you can also check that the number of edges is equal to 9. And so what we're going to do now is do a similar argument. So let's suppose it is planar. Meaning, well, of course, the picture I drew here is there's obviously lots of edges crossing. But remember, in order for it to be planar, there just has to be some way to draw it with no edges crossing. So let's suppose there's some way to draw it, which is not the way I drew it here, in which there are no edges crossing. Then again, by Euler's formula, right, we would need the number of regions is equal to the number of edges, which is 9, minus the number of vertices, which is 6, plus 2. And so there would have to be 5 regions, right? And so now if we look at the average degree of the regions, remember this is this quantity R bar, which I'm going to call 2e divided by, which I'm going to call R bar. And we saw before that this is equal to 2e over R. And in particular, this has to be equal to 18 over 5. And of course, since 18 is smaller than 20, 18 over 5 is smaller than 4, strictly smaller. And therefore, there has to be, well, if the average region is smaller than 4, using the same argument that we saw in part 1, if the average is smaller than 4, it implies that there has to be at least one region of degrees smaller than or equal to 3. Right. Right, and so I'm going to claim now that this can't happen either, because the graph is bipartite, and we'll see why. Right, if the graph wasn't bipartite, it would be possible for there to be a region of degree 3, for example, but we'll see why that. Right, so what does it mean for the region to have degree 3? It means there are exactly 3 edges that bound the region. For example, maybe this is my region R. But let's suppose we had something like this, and let's look at a coloring, right? So if I color this vertex red, well, remember this graph is bipartite, so the red can't be connected to another red. So this vertex has to be blue, and then also this one has to be blue. But then I have two blue vertices which are forced to be connected to each other, and so this is not bipartite. And so if this picture appeared somewhere in the graph, then the graph wouldn't be bipartite, but we're assuming that it is bipartite, right? And so therefore, the degree of the regions has to be bigger than 3, right? And so once again, we didn't show that there's something wrong here. What we showed was that if we assumed K33 was planar, then we would derive some kind of contradictory statement. And so therefore the assumption was wrong, and it follows that K33 is not planar, right? Right. And so remember, in both cases, we use this notion of the degree of a region, which is, it turns out to be an important quantity, although it's not initially obvious why you would want to define this. And then we also used Euler's formula, right, which we proved last time. Okay, and so there's a few remarks I want to make about what we just saw. So the first note is that suppose G is a planar graph with more than 3 vertices. So using an argument similar to what we saw in the proof of part 1 shows that the degree of each region has to be at least 3. And so keep this in mind, because this is going to show up in a few minutes later in the lecture. Right, and to see why this is the case, just go back and look at the argument that we gave for K5 for the complete graph of 5 vertices, and right. And another thing that's worth pointing out is that in this example, if you look at these inequalities, right? So the issue was, for example, in part 2, that I had a region of degree 3 potentially. If I had a region of, if I could only conclude that the degree was less than or equal to 4, then this argument wouldn't have worked, right? Because the only reason we got a contradiction was because we had something of degree 3. And so maybe every region has degree bigger than or equal to 4, and then there's no contradiction anymore. And so it turns out that this kind of quantitative thing that we saw, where it's just barely giving us enough room to get the contradiction, well, there's a geometric way to picture this, because it turns out that these graphs kind of barely miss being planar. And so you can draw them with only one edge crossing, right? So they miss by just one edge. And so I'll show you how to do that. Right, so they're not planar, but they're barely not planar. They're not planar in like the minimal way possible. Right, so let's look at K5 with only one crossing. Well, we have the 5 vertices here. So I'm going to connect them like this. And then I'm going to connect these two. And now to connect the remaining, I'm going to use arcs outside. And remember, you're allowed to use arcs for the edges when you draw them. So I'll have an arc from here to here. I'll have an arc from here to here. And then finally, well, there's 2 more vertices I have to connect, and this is where the edge crossing is going to appear. I'll have an arc from here to here. And so this is the edge crossing, just the one edge crossing. And you can check that this is a picture, a representation of the complete graph, because if you pick any 2 vertices from the 5, you can find an edge between them. So this is the complete graph on 5 vertices, or more precisely, it's an isomorphic graph to what we usually draw K5 as. And there's only one edge crossing. And similarly, you can also draw a version of K33 where there's only one edge crossing. And so what does this look like? I'm going to draw it like this. Right, and so I'm going to connect this to this and this to this. Sorry. Right, and I'm going to connect this to this. And now I'm going to have 2 arcs. So one arc will do this, and then another arc will come up to here. And then finally, I need to add in 2 more arcs. So I need to connect this vertex to here. And then, so far there's been no edge crossing. I just need 1 more arc to complete the picture. And this is where the edge crossing will show up, right here. And so this is, again, the edge crossing, right? And you can check that this is bipartite, right? So let's do this by coloring. Right. Right, so if I color those blue and then the remaining red, this is bipartite. and you can check that it has exactly the edge relationships that you need, right? So there's no red connected to a red, and there's no blue connected to a blue, but each of the reds is connected to every other blue, right? So it is K33. Okay, and so I want to end the lecture today with a theorem which builds on some of the ingredients we've been talking about so far. Another theorem about planar graphs. And so let's suppose that G is a simple planar graph with n vertices, where n is bigger than or equal to 3. And so there's two properties of the graph that we can deduce. So the first is that G has to have less than or equal to 3n minus 6 edges, right? So the assumption that it's planar with n vertices automatically implies that you can only have this many edges. And then the second is that G has to have at least one vertex of degree less than or equal to 5. And so we're going to prove both of these using Euler's formula. And this kind of shows you how powerful this formula is, because we're not drawing any picture. You'll see we're not going to draw any pictures to do this, right? We're just going to use the fact that assuming it's planar, but generally it can be sort of very, very large and complicated looking graph. But as long as it's planar, then we have this restriction on how many edges there can be, which kind of makes sense that there's going to be some restriction, because if you're allowed to freely add as many edges as you want, it's probably not going to be planar as soon as there are enough vertices. But it is a little bit surprising that you have such a precise estimate that works in general. And then the second part of the theorem is that, which is also kind of surprising, is that no matter how you draw, or no matter how big your planar graph is, there always has to be at least one vertex which has small degree, or degree smaller than 5 in particular. Right, so let's prove this. And so let's begin with part 1. Well, for this, we're going to remember this note from earlier, the note on the top of this page, that if it's planar and you have more than 2 vertices, then every region in the graph has to have degree at least 3, right? So recall that the degrees of the regions are all bigger than or equal to 3. Right, and so remember we had this count for if R is the number of regions R. Remember we had this count where this was I had the number of regions of degree 1 plus number of degree 2 plus number of degree 3, and so on. Right, but if the degrees are all bigger than or equal to 3, then the first two terms aren't there, right? So there's no region of degree 1 or 2, so those are 0. We also had this version of the handshaking theorem where if I added up twice the number of edges, this was the sum over all the degrees. And one way to write this was, well, the number of regions of degree 1 plus 2 times the number of regions of degree 2, because their degree is 2, plus 3 times R3, plus 4 times R4, and so on. But once again, since R1 and R2 are 0, these terms are going to be 0, right? And so notice in particular, if I look at, let's say I multiply the number of regions R by 3, well, this is 3R3 plus 3R4 plus 3R5, and so on. Well, the number, or this quantity below it, is strictly bigger than that, right? And so in particular, if I look at, by comparing these two equations, you can see that if I look at 2e minus 3r, that this is always bigger than or equal to 0, right? And so we're going to use this along with Euler's formula to prove part 1. Right, so let me just copy this over. So I have 2e minus 3r bigger than or equal to 0. Well, if I plug in Euler's formula, remember the graph is planar, so I'm allowed to do that. Well, let me plug it in for r. So I get 2e minus 3 times, right, remember r is e minus n plus 2. right? Because v is equal to n because there are n vertices. So I get 2e minus 3 e minus n plus 2. This is bigger than or equal to 0. And so now let me expand this out. So this is 2e minus 3e plus 3n minus 6 has to be bigger than or equal to 0. Well, I get a negative e. And so this tells me now if I rearrange the inequality that e has to be less than or equal to 3n minus 6. But e is just the number of edges. So this is what we wanted to prove, right? So this proves part 1. Right? And so now let's prove part 2. So for part 2, we're going to give an argument that's similar to some of the previous arguments today, except instead of working with the average degree of a region, we're going to instead use the average degree of the vertices. So I'm going to let's say D with a bar over it be average degree of vertices. On the graph. And so in particular, D is going to be the sum over the degree of each vertex divided by the number of vertices, which is n, right? So this is the number of vertices. Right, and so remember, well, by the handshaking theorem from like the first lecture, if I sum up the degree of all the vertices, that's twice the number of edges, right? So the average degree is 2e over n. And now if I use part 1, right, let me use the inequality from part 1 here. Well, I know that e is less than or equal to 3n minus 6, so 2e is less than or equal to twice that. Right, and so the average degree has to be less than or equal to the quantity that I get here, which is 6n minus 12 over n, which is, I can simplify to 6 minus 12 over n. And so in particular, the average degree is less than or equal to, what did we get? 6 minus 12n, 12 over n, sorry, which implies that the average degree is strictly smaller than 6, right? So with a strict inequality, not just a less than or equal to, right? And so since the average degree is less than 6, there has to be a vertex of degree less than or equal to 5. Right, so there has to be some vertex, let me call it V star, with degree of V star less than or equal to 5. Right, and so that's basically the end of the argument. Remember, why does that have to be the case? Well, if the average is less than or equal to 5, or sorry, if the average is less than 6, it's just the fact again that if the average is strictly smaller than 6, then since the degree of the vertices are integers, there has to be at least one vertex of degree less than or equal to 5. How could this fail? This could fail only if all the vertices had degree bigger than or equal to 6, right? So otherwise, all vertices have degree bigger than or equal to 6. But then if every vertex had a degree bigger than 6 or equal to 6, then the average would also have to be bigger than or equal to 6, right? So the average D bar would be bigger than or equal to 6, right? And since we showed it's strictly smaller, it means there has to be some vertex with degree 5 or smaller, right? And so that's the proof of 2. And so that completes the proof of the theorem. Right, and so those are the main things I wanted to mention related to some applications of Euler's formula. There are a few more arguments like this that are in the book as well, and in the chapter 10.7 in the textbook, which may be worth looking at. Right, and so for the next lecture, I think we're going to skip section 10.8 in the book, which is all about graph colorings, just because we're running out of time, and we'll start talking about trees in a little bit more detail, which is chapter 11 in the book.